Going so far, so early. Okay, so I've been asked to list some references. Here are some books that I have used to prepare these sequence of lectures, and then there is an article by Sawin that contains a very detailed account of the proof of modularity and exactly the construction of these modular tensor categories that I've been sketching through all these lectures. So let's see. So far we have constructed the quantum group. It's a Hopf algebra along with an R-matrix, which is an element of UQG. Tensor UQG, actually we've seen that the formula for this R-matrix involves dividing by Q factorials, and that was not good if we want to be able to specialize at root of unity. And there was a solution, which is to add divided powers of the raising and lowering operators. So actually we're changing our Hopf algebra. And that Hopf algebra, again, has all the same features as the previous one, except those particular denominators are now, have now disappeared. And therefore, it is unproblematic to make sense of that at root of unity. And therefore, one gets a category, the representation category of, let me denote it like this. And that category is now a braided category. Well, it's not yet the fusion category that we're looking for. There's two more operations that need to be performed on that. One of them is to specify that we actually don't want to look at all modules. For example, these Weil modules, we don't want to look at them. We only want to look at tilting modules. So okay, so let me denote by tilt the subcategory of the representation category that consists only of tilting modules. And that thing, well, that thing is still not semi-simple. It still has all these tilting modules with weird filtrations. And then there's an operation that I'll explain later today of modding out that category by some equivalence relation. And that has as effect to both make the category semi-simple and make the number of irreducible objects finite. So that is the category which in Chris's talk is denoted Z of S1. So Z is the 1, 2, 3 TFT, and then the value on S1 is that category. So that was a sort of overview of where we are. But let's see, there's one structure on this that I haven't talked about, namely the ribbon structure. It's like I haven't really told you how to build the ribbon structure in the case of quantum groups. And that's what I want to focus on right now. For that ribbon structure, it turns out that I don't really need to, I mean, we can do it for a Q generic and then specialize to Q root of unity. It doesn't really matter. So I will do it for Q generic. And you'll see that it works just as well when Q is non-generic. So let me recall the definition of a ribbon category. So suppose that we're giving a braided category and that every object has a dual in that category. So that's the setup that we have here. If you look at the category of modules for that, then given the R matrix, you get all that structure. To make C into a ribbon category, we need an extra piece of data. That's called a twist. And Chris talked about it already. A twist is a natural transformation from the identity functor to the identity functor on C. So if I have a braided category with duals plus such a guy satisfying some axioms, then that's called a ribbon category. Having an identity, having a natural transformation between the identity and the identity, well, that's a sort of cumbersome way of saying the following. It's saying that for every object, X, there is a map, a morphism in this category, from X to X, and that's theta sub X. So that's what it means. There's also a little diagram. If I have X and a map to Y, then I can do theta X and map to Y, or X to Y and then theta X. That should commute. So in order to list the axioms, I'm going to use a graphical notation. It's denoted graphically. So if this strand corresponds to the object X, I'm going to put a little something, little squiggly here in between. And that means that I look at the map theta X, which is a map from X to X going downwards. The axioms, I'm about to define the notion of a ribbon category, which Chris told about already. Let's see. Okay. So the twist needs to satisfy the following axioms. First one says that if I have two strands and I do the twist on these two simultaneously, that is the same thing as doing the twist on one, the twist on the other, and then a full braiding. And if I want to write an equation for that, the equation is as follows. Theta sub x tensor y equals beta sub xy composed with beta sub yx composed with theta x tensor theta y. These are the two betas, these are the two thetas. So that's one axiom. Here's another axiom. If I have the dual of an object, let's take the right dual. and I do the twist on it, that should be the same thing as, well, you do the twist on the object x itself, and then use the duality structure to go back to a map between right dual of x to right dual of x. And as a formula, that's the following. Theta sub right dual of x equals co-evaluation tensor 1 composed with 1 tensor theta x tensor 1 composed with 1 tensor evaluation. If I want to be precise, the co-evaluation is here, so that's a co-evaluation for x. That's also the evaluation for x. And that's the identity on x star, and that's the identity also on x star, and all those two. And finally, Chris already talked about that also. There is one that looks as follows. So here I start with x. Twisting it that way goes to x dual. Twisting it once more goes to, so this is labeled by x double dual. And then this is again labeled by x dual. And this is again labeled by x. And so it makes sense to, I mean, this is a map from x to x, and therefore it makes sense to ask that it be equal to, for example, the square of the twist, as I'm asking here. Let me write it in formulas. 1 tensor co-evaluation times beta tensor 1 times 1 tensor evaluation times co-evaluation tensor 1 Okay, let me put all the labels. So we read from bottom to top. X, here I have the co-evaluation between x double star and x star. So I'm going to put here x star as an index. Here I have the braiding between x and x double star. Let's see if I'm being consistent. Yes. Here we have the evaluation of x. Here we have the co-evaluation of x. Here we have the braiding of x and x double star. And here the evaluation of x star. So, I mean, here you see why this notation is somewhat superior to that one. Which is that here it actually makes sense that if you twist things around that way, you get something that you can re-express. Yes?
This formula makes us think of a special case where you have only one twist in theta. Is there such a case? Suppose x double
Theta is a morphism from x to x. And if you have only one twist, that's a morphism from x to x double dual.
Yeah, suppose x double dual is x.
That never happens.
Never happens.
That never happens. In the case of quantum groups, the double dual is, well, it's the same underlying vector space, but you twist the action by the square of the antipode. So, and in those cases, the antipode does not square to 1. So it's, I mean, you're right. It's the same vector space, but the action is different. So in particular, the identity map from that vector space to itself is not a map of UQG modules.
So would be sufficient antipode square equals 1?
Well, we don't want to impose that condition. It's not satisfied in the example we care about. You're thinking in less general terms because you want to impose a condition that is, yeah, so I don't want to impose that condition. I mean, of course, you can go and like write down whatever equations you want and then study them. Nothing, but I'm saying it doesn't apply to this situation. So, yes, so let me give you a slightly better graphical notation for ribbon categories. Which is instead of having little strings denoting objects, you have little ribbons denoting objects. So that's the old notation, and the new notation has little ribbons. So, I mean, you know what a ribbon is. It's like a little thin piece that's like, it's a three-dimensional object that I'm denoting like that. It has a thickness in one direction, but no thickness in the other direction. If I have a braiding, then of course that becomes a braiding between these two ribbons. And most importantly, if I have the twist that is encoded by the following thing, so this ribbon, you make it twist on itself and make a full turn. And this way, this side I'm going to shade because the ribbons have, well, they have a coloring. They have a side which is the correct side and a side which is the other side. Here you see the other side. You're not allowed to end with the other side. You always need to end with the correct side. And then, so that's the elementary operation you can do. And then those axioms that I drew this in this way actually become more intuitive if you rewrite them using that notation. So let me do it for the first one. So here, on the left-hand side, we have two ribbons that are next to each other. So imagine that you have two ribbons that are sort of put parallel next to each other, and then you do a twist on that. So you sort of have them go like that, and then they continue and do the full turn and then come back. So let me try to draw that. I'll need more space. So this one here comes on top. And then that one will come on the bottom, and then it's that one that comes on top, and that one goes on the bottom. Here in the middle, we again have two ribbons, but they're both in the, showing us the shaded part. This ribbon twists here, like that, And the other one, well, it comes here below. It also twists. So in some sense, this comes in front, and that comes in front, and then the other is sort of back there. But here, really, this part is in front, and the other part is in the back. And this part is in front, and the other is in the back. So that's a three-dimensional object. It sort of goes around like that. And, well, we can do an ambient isotopy to bring it to the following shape. So these two ribbons, they do two different things. They do a full braiding, and then they each one do a full twist. And here I've separated the braiding and the twist. The twist comes here, and then the braiding comes there without any twist. These two things are the same. So that's a justification for this. That one, well, you can imagine what happens. It's like you sort of either have a piece of ribbon that goes and then twists, full twist. I can't do full twist very well with my hands. Or it goes there, comes back, does a full twist here, then comes back. And if you take those two things and like take this one and pull it straight, you'll see that you get the same as that. And then finally, well, I could redraw this one using that formalism. It's pretty obvious what I would do. Here it's a ribbon that's completely flat. It's flat, it goes around in the plane, and then again turns in the other direction, making sure to where it goes up and down. And then if you do that with an actual physical piece of ribbon and you straighten it out, you will see that you get two full twists. You get twice this. And so that's something that you then impose as an axiom. More generally, in a ribbon category, any ribbon tangle, any such picture that you might want to draw can be interpreted as, I mean, if you label the various ribbons by objects, then any such picture corresponds to a morphism from the tensor product of the objects on the top to the tensor product of the objects on the bottom. And these axioms are, well, it turns out that these are exactly the axioms that you need to impose so that anything you could possibly do in 3 dimensions becomes an equation in the category. So here I've imposed this equation and that equation and that equation, but it turns out that this is exactly a set of generators so that anything that you can do in 3 dimensions becomes an equation in the category. Okay, so the goal for today is to construct examples of ribbon categories starting from a Hopf algebra with an R-matrix and with an extra piece of structure that's going to correspond to this guy. So let me state it as a theorem. Let's see, I guess I'll do it here. So the Hopf algebra has an R matrix. So the R matrix is an element in the tensor product of two copies of A. And I'll remind you what the axioms of an R matrix are. By the way, this very first axiom here is something that I completely forgot to show yesterday when I was proving that, when I was constructing an R matrix for UQSL2. So, well, that is something that also needs to be shown. Okay. So it's equipped with this, and also equipped with a charmed element. So the charmed element is denoted mu and is an element of A, and it satisfies its own set of axioms. So here they are. S square of A equals mu A mu inverse. Then the multiplication map applied to the product of this with R should be the same thing as the multiplication map of the product of one with mu. So here's an inverse. Here there's no inverse R bar. So R bar is just R where you switch the role of the first and the second coordinates. It's the twist applied to R. I guess if I wanted to be consistent in notation, I would call it R sub 2, 1. So that's one equation, and then we have some other easier equations. So S of mu equals mu inverse, and delta of mu equals mu tensor mu. And I can already say that this particular element is going to be important, so let me call it nu. Nu is the so-called ribbon element that's going to produce for us the ribbon, the full twist. Okay, so this is the data that we have. Let me finish the statement of the theorem. Then the category of finite dimensional representations of A, which I just denote rep A, is a ribbon category, satisfies those axioms. Well, there's a way of defining the twist, which will involve this element nu, and with that definition, it satisfies those axioms. Okay, let me spend a few minutes telling you what these a little bit about those axioms. The first axiom for R, this one here, just says that if you use R to construct a map from, say you have two modules, x and y, and you want to construct a map from x tensor y to y tensor x using R, well, this first thing is what guarantees that this map is a module map, is equivariant with respect to the action of the algebra. This has a slightly similar status. It guarantees that if you take this element mu to make a map from, well, an object x to itself, well, you shouldn't view it as an object to itself. You should view it as a map from x to the double dual of x, and then it's equivariant. It's an A module map from x to the double dual of x. It's just a little bit confusing because the underlying vector space of the double dual of x is the same as the vector space for x. It's just the algebra action is different. Sorry?
Just repeat the last statement. So this mu, you need this as a map from
so let me.
double dual, but with which condition?
Okay. So if I want to define the braiding, so the braiding from two objects that's defined to be, well, these are just vector spaces with some given actions. So I can use those actions to have the R matrix act on them. And then I have, again, these two vector spaces that I just permute because they're vector spaces, I can permute them. This you can always write down. But this is not always going to be a map of representations. For it to be a map of representations, you need that equation. So this is the braiding in the category. Similarly, I can define the twist. Sorry. I'm going to define a map from x to x double dual, which I call mu. So this is a map from this vector space to that vector space, which is defined to be, well, it's just mu that acts here, this algebra element. So we start with x. What is x double dual? X double dual is a new module. A module is given by a pair of a vector space and a homomorphism from the algebra to the endomorphisms of that vector space. The vector space here is the same as the vector space there. The algebra homomorphism from your algebra to the endomorphisms of x is twisted by s squared. Putting a star twist by s, putting the double star twist by s squared. And saying that this is an algebra homomorphism, if you write down what it means, that's exactly that equation. Sorry, saying that this is a modular homomorphism, from saying that this, asking this to be a modular homomorphism.
But if that's a morphism, isn't that an isomorphism of modules between x to x star to x double dual?
Yes, it's an isomorphism, that's one isomorphism. There's another isomorphism you can build using mu inverse. They're not the same, and they're sort of on equal footing. So it doesn't make sense to say they're the same, because they're different, and there's two different ways of making them isomorphic. If you say they're the same, you sort of give a big preference to one of these isomorphisms as opposed to the other isomorphism. So you shouldn't say that they're the same. You should say that they're different, and there's an isomorphism between them. So this is so these are A module maps. That's what these two axioms, say. These axioms here, well, Chris talked about them quite a bit. I mean, they correspond to the fact that if I take two parallel strands and braid it on top of something, it's the same thing as taking first one and braiding it and then the other and braiding it. What I will do is actually write down this thing just in just like not do anything and write it in graphical notation. Let's see. So I had used blue, so let me write blue again. So this is, if I have R, and I do the coproduct on R on one leg, that should be the same according to the first axiom to the following. Okay, so that's the first axiom for, well, that's this axiom for R. And then we have another, the second axiom looks as follows. These are the things that I'm later going to be manipulating. I find them more handy than the notation that just like puts everything in one single line. Okay, let me also draw a picture for this one. So that one does the following. It says I have R here, mu inverse. I multiply them all together with mu inverse in the middle. That should be the same as R bar, mu in the middle, and multiply them all together. So for example, you see, using this picture, this notation, you see that this expression is actually quite left-right symmetric, which is completely obscured by this notation. Here you have the feeling that you put mu inverse on the right, but actually, well, here I use a multiplication, there I use a multiplication. These two multiplications are denoted in very different ways, and if you actually work out what this means, this is what it means. Okay, so let me tell you why you might want to put this axiom. I mean, there's a very good reason in terms of these kinds of pictures why this axiom is a reasonable thing to impose. So what we want to do is, starting with this piece of data, starting with you are given an isomorphism between X and X double dual, and what you actually want is to construct a twist theta. That's what you want. So how do you construct this, which is a map from X to X, given that, which is a map from X to X double dual? So here's one way that you could go about defining it. You define theta sub x. So or let me say it like that. Definition 1. So I put mu here. And let me be careful and label things by what they are. This is x. This is again x. If I have such a kind of duality, I land with x with a star on the left. That's the left dual. If I have this kind of picture, I have x with an arrow on the right. And here I have an isomorphism between this and that. So that's mu sub x with an arrow, with a star on the left. So that's one way that you could define this using that. Here's another way you could do it. You could say, let's have the twirly go on the right side. So this is what you get. Now it's going to be a mu inverse. So this is x, this is x. That's the other kind of dual, namely the right dual. That's the left dual. And that's so that's mu sub x right dual, all that inverse. So, yes?
Why not recompose this diagram that you had there, cut below or bottom, and know this? I mean, you were asked that
Which?
question along. Yeah, that one. There's a double dual there.
Here.
Yeah, so recompose this bottom part with mu.
That's yet another thing you can do.
Oh, that actually works.
So, to show that this equals that, you need this axiom. To show that what you're suggesting is equal to, well, I'm not sure which one, like one of them. For one of them, you don't need this thing. So there's like, you're suggesting something that's also completely reasonable, and it's equal to, and I cannot do it in my head right now. Well, I think it has to do with like which way the loop is. If the loop is on the left, then it's going to be equal to the one with the loop on the left. But there's no way of ever taking a loop on the left and making it be a loop on the right. Writing it that way has the advantage that it makes it, if you work out the algebra, you get exactly that equation. If you do what you suggested, then you need to do a little bit of extra work to see that it's actually equivalent. So let me work out those definitions, see what we get. Okay, so how does one define? So this is mu acting on a left dual. This is defined in the following way. We make a little squirrely and then precompose with S inverse and let it act here in the middle. And then here we have an R matrix that is defined using this. So we have the R matrix here. So that's just unraveling the definitions. Then you can actually take this string and pull it straight. I guess that's not completely obvious that you can do it, but if you sort of well, for example, here I have a zigzag that goes up and down. I could take that zigzag and straighten it. Eventually, here I have a zigzag that goes down and then down again. You can take that and straighten it. Eventually, what you get is the following. So, first of all, S inverse of mu, that's mu inverse. That's this equation here. So here I have mu inverse acting. And you need to keep track of the order in which you encounter things as you follow this. So you encounter first the right leg of R. So R with its right leg. And then I encounter this guy, and then I encounter the left leg of R. So this is what you get.
The axiom, the S inverse of S
It's equivalent. S is an algebra anti-homomorphism. And therefore, if S of A equals B, then S of A inverse is B inverse. And then S inverse of B inverse is A inverse. Okay, same little exercise here. Have a braiding. That's an R matrix. Note that it's a braiding between X and X. So I don't need to precompose with any kind of... If it was a braiding between X and the, say, double dual of X, I would need to put an S squared on one of these legs. But here it's braiding between X and X. Okay, so this is what we have. On that side, there's a little thing precomposed with S. There's a mu inverse. It acts here in the middle. It goes here and there. Again, you can straighten this whole thing out and write what you see in order. Well, here in the middle, you'll see S of mu inverse, which is just mu. The first leg of R that you encounter is the left leg, and the second is the right leg. And therefore, it's the same thing as having R with the left leg going there and the right leg going there. But I'll just rewrite it by putting a bar here and define R bar. So R bar is by definition just R with the two legs twisted. So now if I want to write this as the action of a single element of my algebra on this thing, well, I need to multiply these three things together, and you get this. And here, you multiply these three things together, you get that. And the equation that says that this equals that is exactly that equation in red. So the meaning of that equation is that those two natural definitions agree. Those two things that you might naturally try are the same. Okay, so I've explained a little bit why you want to put all these, well, at least this this thing here. Now I can define the twist to be nu acting on X. And, well, if you take nu to be this, you get definition 1. If you get nu to be that, you get definition 2. But I just denote it like that, and I'm not making a distinction between these two definitions. Okay, so now we want to prove this, that, and that. That's our goal. I can't do it right away. I need to prove some lemmas before. So bear with me. Okay, I guess I don't need this anymore, but I do need everything else. So I'm sorry, but I'm going to erase these. Okay, well, these are two equations. I'm going to prove only one. The proof of the other one is completely analogous. The proof goes as follows. Well, that's an invertible element. That's one of the axioms of an R-matrix. This is an algebra homomorphism. Therefore, the image is invertible. So I'll show that it's equal to its own square. And if an invertible element is equal to its square, then it has to be equal to 1. The proof goes as follows. This is R with an epsilon stuck there. That's the same thing as if I co-multiply my little epsilon into an, and then apply epsilon. Tensor epsilon, now I can use this axiom to that situation, and I'm left with that. Well, that's exactly what the statement is. This element is equal to its squared. So that's the proof. Now I need a second lemma. That if I apply S on both legs of R, that I get back R. And the argument is going to go as follows. Namely that S tensor 1 applied to R is a right inverse of R and left inverse of S tensor S applied to R. Well, so if I have these two elements and the inverse of this is equal to the inverse of that, then these elements are invertible. Actually, a little comment, which is interesting. So if I didn't impose that R be invertible, and I wrote this axiom as delta op A times R equals R times delta A for all elements of the Hopf algebra, actually that's the formula that I'm going to use in that lemma. Then you can use this lemma too to prove that R is invertible. Because, well, here, I'm constructing a right inverse. and that right inverse has a right inverse, and then it's a standard algebra trick to say that if you have a right inverse and that right inverse has a right inverse, the element is invertible. So invertibility of R is not strictly needed as an axiom. Okay, so I've started the proof there. Now let's see, this belongs to that. So let me first show that this is a right inverse to that. So here's how it goes. I take R and multiply it on the right with R with a little s. On this leg. So now let me emphasize a piece of this diagram on which I can apply one of these axioms. This piece that I emphasized is exactly that, and therefore I can replace it by this. You get this by the antipode relation. That's exactly that, and that's 1 tensor 1 by the above lemma. Okay, now that I'm saying it, there's something that crosses my mind, which is that maybe I said something wrong. This lemma uses in its proof that R is invertible, and now I'm using in the proof of lemma 2, I'm using lemma 1. So I guess I have to take back what I just said 2 minutes ago about the invertibility of R being automatic. I mean, it might be, but I'm just realizing there's a little loop in my reasoning. So, okay, so that proves one of the assertions, and then the other assertion is equally straightforward. And this here, I'll just leave as an exercise. I mean, you end up using this one. You can just do it. There's nothing difficult. Okay, so now let me go back to this theorem and prove the theorem. Now that I have these lemmas, I can just do it. Okay. So we want to prove 1, 2, and 3. Here's 1. By definition, this is equal to mu two strands coming out. Mu acting on a tensor product of two things, well, that uses the coproduct on mu, and the coproduct on mu is given as mu tensor mu. So that's the same as mu here and mu there. Okay, and now it's just a matter of pulling the strings to bring it into that form. So let's take this little loop and push it upwards. So here it is. And then that bigger loop remains where it was, and this strand goes through it. Okay, now let me take this and redraw it in this slightly different way. So I have mu here, that's the little loop. And I'm going to have this guy go on the other side. Of that. So I just took this strand that was going straight through and pushed it so that it goes to the right. Now I take this little loop and bring it up, and then we're left with exactly what we wanted. And here I have these two things. So that was completely easy. Two amounts to checking that the antipode of nu is nu. Here we act by nu, that's this definition. Here we act by including a little twirly and putting the antipode of nu. Sorry, I guess think of it as here being y and here being the dual of y. It's going to be the right dual of y, so I will act with the antipode inverse of nu. So S inverse of nu equals nu is what you would get from that equation, but because nu is because S is invertible, this is what one needs to check. So that you can do directly by saying, okay, so I have nu. So nu has a mu inverse that multiplies in the middle, and then I have an antipode, S, that's there. S is an anti-homomorphism of algebras, so I can rewrite this using, so I'm going to have the strands be first like multiply and then like switch everything. And then I have S here, S there, mu inverse, R. That's the same thing if I put the, well, S acting on mu inverse is just mu. That's one of the things we know. And this, I can rewrite it as having the crossing happening on top. And then I have two copies of S. But that's this lemma that says that two copies of S do nothing on R. Well, that's exactly the other definition. That's mu, and here R bar. So that's OK for number 2. And finally, let me do number 3. Number 3 looks like it might be the most complicated one to check. And if you do it the wrong way, it ends up being the most complicated one to check. I can say by experience over the last couple of days where I was like fighting to figure out how it works until I realized that I was being completely stupid and that you can do it in like this amount of space. You can do it. So here's how it goes. So the double twist, well, I can use one of the definitions of the twist here and the other there. And if you do that, you end up with the following. So I have mu here, and there I have mu inverse there. That was definition 1, and that was definition 2 of the twist. Well, now you sort of move things a little bit. Let's have this mu happen a little bit below, and then this mu inverse happen a little bit above. like that. Well, now we can let them cancel each other. And now you can well, you can undo this thing. Of having put this loop a little bit higher. So that's it. So we have shown that we actually get a ribbon category from a charmed element. Our next goal is going to be to construct a charmed element for the quantum group, and therefore complete this will complete all the data that you need in order to have your category, your fusion category. We have the braiding so far, and we have the twist that comes from this ribbon, that comes from this charmed element, and that's all the data. So that's going to be next hour.